In 1546, a visionary physician named Girolamo Fracastoro proposed something radical. He theorized that disease wasn't caused by bad air, but by tiny, invisible seeds of contagion he called seminaria. Fracastoro imagined these seeds were physical particles capable of spreading through contact or even over great distances. He correctly identified the mechanism of transmission long before anyone could ever see it. The theory was brilliant, yet it faced a massive barrier. The technology to observe these tiny particles simply did not exist. For scientists of the 16th century, the invisible world remained a concept, not a reality. This set the stage for a century-long search, driving thinkers to invent the very tools that would finally pull the curtain back on the microscopic frontier. The simple microscope is a marvel of early engineering. It consists of a single, powerful lens used to bend light and magnify an image. By passing light through this curve, the lens focuses and enlarges the object, allowing scientists to see far beyond the reach of the naked eye. While they seem basic, these single-lens microscopes were the primary tools for early pioneers. They achieved higher resolution and clarity than many complex systems of their time. The compound microscope represents a clever architectural shift in optics. By utilizing two or more distinct sets of lenses, it allows for a much more complex path for light. In this design, light first passes through the objective lens, which creates a magnified image. This image is then further magnified by the eyepiece lens, which acts as a powerful magnifying glass for our eye. While the compound microscope was a major technological step forward, it faced early hurdles. Historically, early compound models produced images that were actually less clear and more distorted than the high-resolution simple lenses used by pioneers like Leeuwenhoek. Despite these early optical limitations, this multi-stage magnification system became the foundation for the instruments we use in every modern laboratory today. In the late 1500s, in the Netherlands, two spectacle makers named Hans and Zaccharias Janssen experimented with placing multiple lenses inside a tube. This simple act may have sparked the invention of the first compound microscope. However, the Janssen legacy remains a historical puzzle. They operated in a time when craftsmanship was often shrouded in secrecy, and their work was never officially documented for the scientific world. Because their observations were never published or verified by contemporaries, their specific contribution remains speculative. They represent the pre-scientific era, where technological innovation often lived and died in the workshop. In the world of science, history is written by those who record their discoveries. Take the case of Hans and Zaccharias Janssen. They are often credited with inventing the microscope in the late 16th century, yet their story remains a mystery. Without published records, their contribution stays trapped in the realm of speculation. Compare this to Robert Hooke or Antonie van Leeuwenhoek. They didn't just observe, they published. Their consistent reporting to the Royal Society turned niche observations into scientific truth. In science, if you don't document it, it simply isn't official. Robert Hooke was a brilliant 17th century polymath whose curiosity unveiled a hidden realm. His observations challenged the limits of the human eye. In 1665, Hooke published his masterpiece, Micrographia. It was a landmark publication that brought the wonders of the microscopic world to the public eye for the first time. Micrographia became a bestseller across Europe. It ignited a firestorm of scientific interest and redefined how society viewed the natural world. Through his detailed illustrations and meticulous documentation, Hooke invited everyone to look deeper, effectively bridging the gap between scientific discovery and the public imagination. In 1665, Robert Hooke turned his microscope toward a thin slice of cork. What he saw was unlike anything documented before. Under the lens, he discovered a repeating structure that reminded him of a honeycomb. He called these structures cells, as they resembled the small, empty rooms where monks lived, known as cellula. Hooke was looking at dead plant tissue, observing only the rigid cell walls that remained, giving the cork its structure. Galileo Galilei is celebrated for looking upward to the heavens. Yet the same scientific curiosity that drove his telescopic discoveries also led him to explore the invisible world beneath our feet. Galileo applied the principles of compound lenses to examine the complex anatomy of insects. By revealing the intricate structures of their wings and eyes, he demonstrated that the same laws of optics applied to the smallest creatures. His work confirmed that the pursuit of the invisible world knows no scale, bridging the gap between the vast cosmos and the microscopic life surrounding us. Antonie van Leeuwenhoek was not a scientist by trade. In the 17th century, he was a merchant, selling high-quality fabrics in the Netherlands. To inspect the quality of his textiles, he began crafting his own lenses. He pushed grinding techniques to the limit, creating tiny, simple lenses with unmatched clarity. By looking through these superior lenses, he saw what no human had seen before: a hidden, living universe inside a single drop of water. This fabric seller transitioned into the father of microbiology, forever changing our understanding of life itself. In 1674, Antonie van Leeuwenhoek shifted his focus. Moving beyond static samples, he examined a drop of pond water under his powerful lens. He discovered a world teeming with life. He saw tiny singular organisms moving independently, which he famously dubbed animalcules, or wee little beasties. This was the first time humanity had witnessed living, single-celled organisms, forever changing our understanding of the microscopic scale. In the 17th century, claims of invisible worlds were met with intense skepticism. To move from curiosity to science, the Royal Society of London sent a formal delegation to investigate Leeuwenhoek's findings personally. This was the birth of modern scientific verification. By witnessing the animalcules together, the community turned one person's individual report into an accepted scientific fact. Collective witness remains the bedrock of science. It transforms personal observation into verified truth. In the early days of microscopy, innovation often lived in shadow. The Janssens, credited as early lens makers, remained largely secretive, leaving behind little evidence of their work. By contrast, Antonie van Leeuwenhoek chose a different path. He sent detailed letters of his observations to the Royal Society of London. Communication became the heartbeat of scientific advancement. Peer review transformed isolated discovery into established science. By inviting experts to verify his findings, van Leeuwenhoek turned his niche hobby into a global scientific legacy. Communication is not just an afterthought in science. It is the fundamental bridge from private mystery to public knowledge. The history of microscopy is defined by two different design paths. A simple microscope relies on a single, high-quality lens to achieve remarkable clarity, as demonstrated by the pioneers like van Leeuwenhoek. In contrast, the compound microscope uses multiple lenses arranged in a sequence. While more complex, this architecture provided the foundation for the sophisticated instruments found in modern scientific laboratories today. In the world of optics, early inventors faced a hidden barrier. They often prioritized magnification, simply making objects appear larger. But real clarity requires resolution, the ability to distinguish 2 points that are very close together. If you simply enlarge an image without increasing resolution, you are left with nothing but a larger blur. This was the bottleneck of early microscopy. Early lenses were often great at zoom, but poor at clarity. True progress came when makers focused on lens quality to sharpen that resolution. Being able to separate 2 distinct points of light is what turned simple glass into a key for discovery. In 1546, Girolamo Fracastoro proposed a radical idea, that disease is spread by invisible seeds of contagion, which he called seminaria. For over a century, this remained a theory. It wasn't until the refinement of the microscope that these invisible seeds could finally be brought into focus. Antonie van Leeuwenhoek looked through his custom lenses and discovered animalcules. He was effectively seeing the invisible agents of disease for the very first time. This direct observation validated the ancient hypothesis of Fracastoro, providing the foundation for our modern understanding of germ theory. The history of microscopy reveals a monumental shift in how we understand life. Early observers like Robert Hooke looked at cork and saw static, room-like compartments, which he named cells. However, this changed when Antonie van Leeuwenhoek peered through his high-powered lenses and saw something completely different: active, moving, living organisms. This was the architectural shift. The cell was no longer just a structural box, but a functioning biological unit. Life was not just built of rooms, but teeming with activity at the smallest scale. A common historical misconception is that adding more lenses always resulted in a better image. Early inventors believed that stacking lenses would simply multiply magnification. However, early compound microscopes were plagued by imperfections called aberrations. Every time light passed through an additional lens, the image became more distorted and fuzzy. In contrast, Antonie van Leeuwenhoek focused on a single, perfectly crafted lens. His simple design avoided these internal reflections, allowing him to see animalcules with startling clarity. Leeuwenhoek proved that precision and quality were far more important than mere mechanical complexity. Sometimes, less is truly more. Scientific progress hinges on one core principle: transparency. In the era of myths, discoveries were often held as secrets, leaving them vulnerable to error and loss. Transparency turns private observation into public knowledge. When you discover something new, you must document it and share it with the world. This creates the verification loop. First, we document our findings meticulously. Second, we share them transparently. Finally, others verify the work, turning a theory into a foundational fact. This simple, disciplined process of sharing is the single biggest difference between the era of myths and the age of modern science. We have come a long way from fearing invisible seeds of contagion. Today, we understand that these microscopic organisms are not just threats, but the fundamental architects of life on Earth. Once, unexplained illnesses were blamed on mysterious particles. Science transformed that fear into a profound understanding of our biological world. By turning the unknown into the observable, these pioneers provided the foundation for modern medicine and biology, forever changing how we view existence.